Hello everyone, welcome to the mining match. Let's start by announcing Spanomine. If you speak Spanish and you work in the mining industry, or you're looking to do business in Latin America in the mining industry, you should join Spanomine. They provide professional development and connections to the Latin American community. Let's talk about what is the cost-effective way of evaluating a mineral deposit in an early stage of exploration. There are thousands and thousands of deposits that requires exploration, and people think about drilling because it's the standards that allow to have a resource. That's what everyone wants to create value. But what happens if you don't have the budget to do this? What can you do before any drilling is done in a mineral deposit? Today, we're going to evaluate a Russian method to assess a mineral deposit before any drilling is done. I have invited our guest speaker, Nadia Yavorskaya, who will discuss about this method. Hello, Nadia. Welcome to the Mining Match.
I'm fine, and I'm ready to present. Today, I'd like to have a talk on a cost-effective way to evaluate mineral deposits. It's a little known use of superficial geochemistry in many parts of the world. This technique was developed in Russia and around 30 years ago, and improving since then. It is a useful method because you can attract investors even on the early stage of exploration. The scientific basis of modern exploration geochemistry for predicting mineralization is based on contrasting between background and anomalous signal. Statistical techniques which define the signal from mineralization involves multi-element calculations, and this shows the better contrast in geochemical anomaly. For example, people use just a single element anomaly, and the signal is very broad. On the left side, you see just one signal which reflects multi-element anomaly. As you see in the legend, it is on the top of the legend, you see all elements which are involved. This technique defines geochemical ranks. Multi-element geochemical halo are the final stage signals from the dispersion of chemical elements in geological environment. Multi-stage deposit forming geological process are reflected in corresponding level of geochemical systems, which named, the name of it is geochemical rank. In different stages, you define different geochemical ranks. For example, in scale 1 to 1 million, you define number 4 geochemical rank is 4, we name it 4. But then you choose another area on the basis of what you defined first. This geochemical rank will be number 3. And then go on. Geochemical rank number 2 will be of the scale of the mineralization zones. which you can see in cross-section. So I can show you how geological systems correspond with geochemical ranks, which are defined during geochemical surveys. The table shows you different exploration stages and corresponding ranks. So multi-stage deposit forming geological process reflected in corresponding levels of geochemical dispersion, which the name of it is anomalous geochemical fields, and in the table you see ranges of geochemical systems. The lowest rank is attributed to the Earth crust in general, and all mineral systems consistently enclosed into each other and correspond with enclosed anomalous fields. The methodology of prediction of amount of metal in the ground is in this slide, I want to discuss the techniques which are successful in exploration in Russia, Peru, and Mongolia. And exploration was either on gold or base metals or PGs. The technology is based on contrasting signals between background and mineralization, as I already mentioned, and predicting amount of economic elements depend on the geochemical patterns. First, you should calculate the anomical geochemical field productivity. This involves size and contrasting contrast coefficient of anomical geochemical field. Then you took into consideration predictive ore thickness, number of sample lines crossing an anomaly, corresponding coefficient between lithology and stream sediments, corresponding coefficient between stream sediments and soils. This is the example of applying this strategy. The case study number 1 is the official evaluation of gold amount in lowland glaciated terrain. This calithorium halo was defined from a regional aerogamma ray survey. This is rank number 4, so it's a regional survey. And the survey was on high ridge terrain. Differences in elevation is about 500, 700 meters. And samples were taken from diluvial sediments and soils. The cover is from 10 centimeters to 50 centimeters. Only several outcrops are on this covered on this territory. After defining the potash anomaly, there was the second stage of exploration. It was done on this defined area. This rank is number 4, and the rank number 4, what is this? We chosen from the rank number 4, the rank number 3. which was defined as gold arsenicum anomalous geochemical field. The sampling was on superfine fraction of stream sediments and soil. Sampling was on ridge tops and slopes. Some quartz rock from slope debris were taken as well. The area is 55 square kilometers, and sampling was done as defined, 12 samples per square kilometer. The hollow, as I said, was defined as gold arsenic for the rank 3. So after all calculations, predicted gold anomaly, predicted gold amount from this anomaly was defined as 108 tons. After that, another survey was done, minimizing the area, taking into consideration already defined samples, but minimizing the scale of the exploration. And you see that resampled area was a lot less. Again, superfine fraction was involved from stream sediments and soils. And sampling interval was 100 to 40 meters. So the area was already minimized to 25 kilometers. The hollow, which was defined, is gold, lead, silver hollow, and the rank of this territory is rank number 2. So calculations showed that predicted amount of gold is 91 ton. After this study, was drilling involved to define actual amount of metal in the core. So there were chosen several areas, number 1, number 2, and number 3. Combined area is 800 square kilometers. And on this territory was done trenching and drilling. So amount of metal estimated here was 32 tons of gold and 242 tons of silver. I should mention that the precision of prediction of metal from the official geochemistry was 90%. So the second case study that I want to show you, it's official evaluation of molybdenum in a lowland glaciated terrain. It's like the opposite of the first case study. There was the mineral occurrence, which is shown as a square, and around this mineral occurrences was done the geochemical survey. This geochemical survey defined the rank of anomical geochemical field number 3, and elements involved in this rank is molybdenum and bismuth. sorry, and lead. So the area was lowland glaciated terrain with the boreal forest, swamps, and bogs. Tills, the thickness of tills were 5 to 50 meters. And soil sampling was performed on borg margins, which you see as dots on the picture. And the area was covered with sampling of 40 square kilometers. So from the geochemical survey, predicted amount of molybdenum was defined as 70,000 tons. Then preliminary study was involved on the basis of anomalous geochemical field pattern defined previously. So as usual, drilling was involved in this stage, and molybdenum resources were estimated to be 127,600 tons of molybdenum. That was defined from drilling. And if you calculate the precision of soil geochemical survey, in this case, it is 55%. So, as summary from this presentation, I'd like to point out that this method that I described allows a pre-drilling estimation of amount of metal in a hidden mineralized zone, and you use surface sediment geochemical data. Method can be used to evaluate prospects for potential economic mineralization. The best results were obtained when sampling soil superfine fraction. And the best prediction precision in all these methods, which is 90 to 95%. Why is that? Because I didn't mention lots of case studies which support that. And the best results, again, are coming if you sample mountain terrain with a high rugged relief. In lowlands with lots of swamps and bogs, the precision of prediction would be about 50%, which is not bad because you still can say that there is metal, and then the drilling, on the basis of that, you can choose if you drill that territory or not. And these calculations are successful for scales of sampling or forming systems or deposit systems. So what was in this presentation? My services, and I collaborate with other geochemists, mainly from Russia. We do these calculations of preliminary calculations of metal in the ground. And if you are interested, you can contact in with what's mentioned here. Alan, do I have a minute?
Yeah. Okay. So if you're finished,
I would like to mention something else.
Go ahead, please.
I had a slide from these two case studies which I presented. there were many geochemical stages involved. And this is not only a 1 year exploration, but nowadays the technology is improving, and I'd like to mention one technology. This is MEFA technology, which allows you to do geochemical surveys from regional geochemical survey to mineral body scale geochemical survey in 1 year. Here you see how it is done. In the picture on the left, you see that sampling are arranged in such a pattern, and automatical XRF device is going from one sample to another. It takes not much of time. On the basis of chosen elements, you already can define the rank 2 or 3 geochemical survey, and then the sample media would be less samples than, of course, from less territory you sample, and then you send it to the lab with the laser ablation ICP, and these little samples were analyzed very fast. As you see, the burn time is low and the burn area is low. So everything can be done in one during field season. And here you are already coming up with calculations of your area of interest, and hopefully you define the amount of metal in the ground. So this is all what I wanted to say today.